Time for another feature implementation. I just got done recording the functionality for this slider, and it is time to implement some bang bang control capabilities. So I've already got this heater timed PWM capability in the system, and that is configurable from the config file, and then it can receive commands for turning on and off. We can change parameters like the set points and the tunings and all of that, change the cycle time. So all of these values respond to the same commands that might update analog output values. But the other thing I want to do now is a bang bang control. If you're unfamiliar with that, let's see, how well can I draw a paint picture? So you've got okay, maybe we just do pencil and so let's say you've got two limits that you want to control between, and you've got a process value. So you want it to the process to increase till it hits the upper limit, and then you're gonna change some output value that's gonna change it. Maybe it still overshoots a little, but then it comes down, and then when it reaches the lower limit, you're turning something back on. Or maybe it's the opposite. Maybe you have something turned off until it reaches the upper value and then turns on when it gets, or did I say that backwards? Yeah. Turns on to bring it down. Like maybe this is cooling and you've got temperature rising. You need to turn on the cooler when it gets to the high limit. Um, Brings it back down and then turns back off once it's on the low limit. Or maybe you're pressurizing some kind of accumulator or some gas volume. So you need to turn on a pump or open a valve to get it up, and then something is going to consume that gas, and then you need to turn it back on. And so this is just really simple. You've got two limits that typically overlap, so you get this little bit of hysteresis zone where things are kind of just closed in or sitting more idle, and then you just keep bang banging between two states. Trying to draw with a trackball is super fun and wiggly. Highly recommend. So yeah, so this is going to be something that comes in this control configuration, just like this. This is what's driving the heater control. Turn that off, as well as this handful of things that are blinking off on the left, and you can see their status showing up here in this other generic GUI. But if I turn this off, we can see it all stops. So normally with a valve and a control and a GUI, you might click it and it turns on and stays on in that state. You click it again, it closes, stays in that state. However, what if you have valves where you only want them to momentarily go to a state? So you can set up pulse control. And what if you want to change that pulse time? Or maybe you need a really low pulse time because you're overdriving on voltage, so you don't want to let it overheat and cook itself. But we'll leave it at 0.3 so we can see it. And then, and same thing over here on this second pulse valve. And then what if you want to sequence the opening of those two valves with a little separation between them? With a single action. This should really be one of these buttons, but that's all right. This is just a Boolean control for now. And then what if you want that to keep happening, like once a second per se? Let's drop this back down. And so these are just small, simple things that do a little bit of time checking, are run in a deterministic manner on theoretically a compact Rio or an embedded system. This is all, of course, running on the PC here, so it's not as deterministic. But you can get pretty good repeatability on this on like a compact Rio down to 5 millisecond iteration periods. But these all stack on each other. They're basically triggered by sending them a command to true. You can turn them off. So let me set this to a really low period. We'll leave that. That's fine. Let's set these to 1 second. And now they're going to stay on for quite a long period of time. But I can shut off this entire chain early That did not. Oh, this turned this off, but this didn't turn these off. Let's increase this to 1 second. And so now the sequence is staying on late. And I can, okay. I don't think I have the sequencing set up to be able to be turned off early. My bad. Trying to demo stuff that doesn't work. This one should work. That's just always going to stay on. There we go. Okay, so that shut off early. the sequencing one isn't set to be turned off early. So yeah, what was I going to say? So this is all configurable in here. This upper one looks like just a normal open-close valve, but behind the scenes, it's got 2 values on it. So the direction and the enable. This might be like a mechanically latching or magnetically latching valve, where you change the polarity you give it and you pulse it to get it to move in that direction. So you'd have to set the direction you want it to move in, then pulse the enable line, and then when you want it to go the other direction, you change the direction and then pulse the enable line. So you can see that happening in these values up here. So there's a little bit of extra functionality behind this valve, but this valve GUI element is still the same exact implementation and logic and configuration as all these other valve GUI elements, but it is happening behind the scenes because of this latched control bit of code that's running in the control application. And so we're going to be setting up something similar to this. So there is a module available in this. So it's in this Volatus control library. There's a DigitalControlModule. And that has some configuration, like how frequently does it iterate, and then for the data that is associated with it, some group information like the group name, what multicast address is it publishing to, what are some of its internal status fields, so we can see how well it's running. And you can run multiple copies of these. Sorry, I had to cough. And you can run them at different rates. So, something like heater PWM, we do not need running at 200 hertz. That would be goofy. It operates on an output time cycle of seconds. So we can run this at 10 hertz and still get pretty good control. And then, yeah, there's a handful of these different types of digital control I've got implemented, and they can do things like activate the other ones. Each one of these accepts a Boolean command the same way that like a digital output value would. And so it's really easy to have a GUI element command a digital output value directly. Let's say you don't need any smart behavior behind it. But then when you want to pulse something, you can send a command to this name instead, and it will do the pulse control on a prescribed channel. And so you can stack up these Lego blocks of behavior and get some complex functionality out of this just via configuration. Except when you need new capabilities, like this bang bang control, which I don't have implemented it yet. So let's go ahead and get everything shut down so we can look at the code, get rid of all the distractions. And so these are implemented. These are classes that inherit from this digital control class. And so here you can see all of the different ones that correspond to what I had in the configuration. Now, the way I like to start this is by starting with the configuration, because that's going to give me my starting idea of what I need to implement. Channel names and group names need to be unique. So we're going to see some places where we set some extra metadata to identify, or we have like a type string to differentiate between some of the different types that are available. Meta fields are special to this configuration library that I've set up, and it is a way to attach descriptive information to elements while still leaving the name itself unique. And then the config library has traversal and lookup mechanisms where you can do searches for elements based on meta fields and values. But we're going to set the type to, this is going to be bang, 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 bang. I'm going to start it off with a default value of 0, which is off. And just for my OCD, I'm going to always list the type first. And we're going to have a couple of, well, one, we need the output channel. And let's just use the pulse 1 channel. So this is the channel. This is the thing that's going to get commanded every time the bang bang needs to set the value on or off. And now we're going to want a handful of channels that allow us to change how this runs. Well, one, it'll be all of the default configuration for it when it loads. And then if we want to, we can set up GUI elements that'll allow us to tweak these live while it's running. So we're gonna, I have the convention of whatever the root name is for the control element. And then we're going to add in a suffix of what this specific value is. And then you can see that always typically exists as a meta field as well. So again, this is going to be a channel name. Channels always get published as a group if publishing is configured, which this is. It does have publishing config. And all channel names must be unique across an entire system and across an entire configuration. So this needs to be a unique name. This needs to be a unique name because it will be a channel. However, we need some way of recognizing that this is a specific type of value that we're looking for. So that's what the meta fields provide. So the obvious ones is going to be what is our upper limit? And this is going to be a value. This is, yeah, okay. This is going to have a default value of, let's say, 4. And then we need the meta information. And the control param type. There's no reason across these different control types, this control param like isn't generally handled. These could be different names each time. Like this could be bang bang param, but just for simplicity and needing to remember fewer names, sticking with the same name. So this is going to be upper limit. There's no requirement that the control param name matches the suffix on these. One of the early ideas I had was just always look in the string of the channel name for what type it is. But then you kind of have to iterate over them till you find the one you're looking for. And whereas you can look explicitly for a specific thing and you don't have to worry about iterating. So it's a little bit cleaner to put a little bit more identifying information in the configuration, in my opinion. Make it a definite lookup. There is a specific, like I said, there's specific functionality in the config library to do metafield lookups. So let's just leverage that. We've got an upper limit, so of course we're going to have a lower limit. And if I was smart, I would just copy and paste this. Now we're going to need another bit of code. So I think we're going to need a couple more parameters. One is when we're below the upper limit, do we command a true value or a false value? Now, I think the way I want to do this is by default. If you're low, we're commanding a true. And once you get high, we command a false. Hee hee, joke. There's a joke in there somewhere. And then if you want the opposite behavior, we'll have an inverted config. So we'll put it in here. And this time I will copy and paste. And then we can set that to 1 if we want to invert it. And if we need to, for some reason, needed to invert that behavior at runtime, we would be able to send a command to change this value. Is there anything else we need? Oh yeah, so this is going to change to output. We need input value. Now, I am going to get a little complex with this because I've already done this with the heater code. But what if we wanted to take the median of some different values? We wanted some sensor redundancy. Or what if we've got a larger system and we're trying to do averaging control over all of them? So I'm going to do the same thing as I did with the heater PWM, is enable you to be able to specify multiple process values. So there's going to be an output, and then we're going to have a process value. Now, the way I did it for the heater is this can be a string or an array. If it's a string, it doesn't even care about the pvcalc value. But we are going to do just a single string for now. And what do I want to update that on? Let's add another one of these guys. This is going to have to go to the next module. And let's do this BBPV1. Actually, no, if I'm doing this, how about, and I haven't tested the median logic yet, let's do this a couple of times. So let's say we've got triple sensor redundancy, and we're going to take the median. Now, I'm basically using these as software variables. So I do have the scaling set to just always set it to 0. So no matter what I want the process value range to be, let's say we're doing temperature and we're going to a couple hundred degrees, or this bang bang might be a couple thousand if we're pressurizing things, potentially. But these voltage outputs, do have limits, typically -10 to 10. So we're just changing it always to, it's going to multiply by 0. So that we don't get any decamex errors when we're trying to send arbitrarily large values. And I'm lazy and just ignoring the scaling. What I will eventually do is set up mechanisms for software channels similarly to all of this. And, those can still get all the benefits of logging, but wouldn't need any scaling information. And yeah, wouldn't need to worry about using a fake output as a value, because that's what I have implemented and can use for my testing before I have those capabilities. So I lied. Let's do an array, pv1, 2, 3. And I'm going to use the same name as before, pvcalc median. I know how to spell. And then, perhaps we want another configuration that has some kind of disable or what state you're going to go to if all of your process values vanish. But won't worry about that for now. So this should give us enough to implement this control initially. So I'm just thinking in my head. I wish I would have kept that paint drying up. Yeah, but let's get started with this. While I'm implementing this, if I think of anything else that's needed, I can come back in here and add it as necessary. Surely I will have forgotten something. So let's get started with the code. So I'm gonna make a new class, and this is gonna be, one of the core ones that's available. If I wanted to, I could start putting this in a different repository, in a different library. But this is good for now. And I've got search functionality built into my class dialog, so I'm going to use it because this class list is kind of big. Let LabVIEW do its things. And then timed PWM control is going to be relatively similar in complexity. So going to take a look at this just for reference. And so I'm going to do the same thing, start with my standard set of folders I like, create our overrides from the class we're inheriting. And if we take a look in the timed PWM control, we're going to see it's got state, and we'll see how this works in a bit. It's got the PID implementation that it's going to use to do the PID. And then there's going to be a whole bunch of index values in here. So if we look at this init control, it is looking up the index of the channel within the group. So trying to figure out, what order does this name show up in the group? So we've got all of these are contained in a group that keeps track of the numeric values for everything that's operating on. Again, even Booleans are stored as a double numeric, inefficient, but it simplifies a lot of the code and data handling. So that's the trade-off I went with on that. But while these are updating, they're getting passed in the value array for that group, and then updating or reading from any values that it cares about, and passing them back out. So these groups, unlike if you've watched the video where I created a slider control GUI handling, that worked with channel objects directly. Whenever we have something that is doing control in output and then publishing that value out over the network, we don't want to be working with the group directly. Under the hood, these groups of data are implemented as by reference with a data value reference. And so anytime we needed to get data in and out of those, it needs to spend just a little bit of time unlocking that reference and gaining access to that. And that could get slowed down if anything else is reading data from that group, or if like the scaling and data processing and logging part of the code is modifying values in that group. So now not only do we have contention, we've potentially got some race conditions. But we want this control code to run completely uninfluenced from other code running in the system as much as possible. So this digital control module is keeping track of the values itself, and then the group is used to read data in other mechanisms and get the data published. So we're not going to be typically directly working with the group, but we do use it to look up the index values. So, for this pulse control, it needs to know what its command channel is, what its parameter channel is, or like some of the other ones that have multiple channel values. It needs to know what index that number is going to be in the array of values for that group. So that's what we're looking up and storing. And then in the actual logic code, it can pull out values from that value array by their index. And so that's how it can do stuff like get the cycle time, get the minimum on time when it's doing some of its logic to decide whether the output should be on or off for this timed PWM heater control, for instance, or pulling out set points. What is the current set point value? And then this removes the need um, for all of the by reference the reference unlocking, and makes this values array localized and following the LabVIEW convention of being by value as much as possible, which has zero chance of contending with any other parallel running code. So we're going to do something similar, and then there are a handful of other values that we'll explore. Some of them are for doing a second step of initialization, which we'll discuss when we get to that point, and then just other internal configuration and state management. So in the Bang Bang control class, we are going to need to keep track of some indexes. So these will be I32s. We're going to need the value index. This is what I'm always calling what is the value of the root channel. And then we're going to want the upper limit index. Let's be descriptive and good developers. Lower limit index. And then the inverted index. Now, actually, I don't think invert would ever need to be changed at runtime. So I'm going to take that back. I'm going to turn this into a normal config field and get rid of it as a parameter. Now, instead of keeping track of the index of it and looking it up from the array every time, we're just going to use this as configuration field. Now that I'm thinking about it, is we do want another configuration item for what is the normal state. And this would probably coincide with the invert field. But this gives us the 4 quadrants of control type that we need. We need to turn something on to raise the value. We need to turn something on to lower the value. But then maybe we're controlling to negative temperatures. And so we turn something on to lower the value, but we still want the normal value to be off. So maybe this isn't necessary. Maybe we could derive this directly from the invert. But this is basically going to be, what do I set the value to when the Bang Bang control is turned off? And that should, not care of what range it's in. So I'm going to put that in just as some defensive programming paranoia. And what else do I need? That should be it. Oh, no. We need... Okay, so we need our process values. Process value names. So I'm going to shortcut that to PV names. Oh, I do not need 2 of those. Now I already have this in the heater control. I am going to duplicate this. Copying and pasting is a valid development strategy when your goal is independent bits of code. I want these to be separate and not dependent on each other. So if at some point I need to update the heater control with some different capabilities than would be available with Bang Bang control, I'm not trying to find creative coding patterns to share the same type definition. Little bit of a rant side tangent. I believe dry programming, don't repeat yourself, is followed too much to the extreme these days. People find really creative ways to have single type defs and never repeat code anywhere. Um, and of course, like with most things, there's probably a middle ground that doesn't increase maintenance burden too much, and also doesn't increase maintenance burden too much. If you dry yourself too much, you're going to have a hell of a time trying to manage the shared code that kind of becomes really unoptimized and um, takes extra code to work around when you do need different behavior versus, okay, I did want this new behavior in 2 places. And as long as it's not 50 places or maybe even 10 places, if it's like 2 or 3, maybe the maintenance burden of duplicating that again a couple of times is lower than when you start having to get really creative with sharing that code and that functionality. So I'm erring on the I'm going to copy and paste, and that's okay by me. If you choose different, that's cool. I've gotten bit too many times with too creative of applications trying to share code too much. Especially when it comes to object-oriented inheritance and trying to put as much shared behavior in parent classes as possible. I will always respond to anybody saying they want to share behavior with inheritance with the Admiral Akbar, it's a trap meme. Okay, tangent over. Now I have this control. We're going to put that in there for that method. So we've got everything that's in here. Oh, no, we don't. I need the output name. And we'll be adding a couple more things in here when we get to the second step of initialization. But for now, let's load this config and get that stuff going. So a couple of details here. Control message queue. This is the message queue for the digital control module that is hosting this digital control component. As you see in the config, it is possible to have, let me collapse these controls groups. You can have multiple instances of this digital control module running. So with this configuration, when the heater PWM is getting instantiated and initialized, that control message queue would be pointing at this digital control module. For all of the controls in this first one, it would be getting the message queue for this instance of the module. And that's if it needs to send commands directly to one of the other controls that are running in that component. It can shortcut having to look up the message queue elsewhere. A lot of these that are meant to output to like digital output channels, which if I selected just the right amount of text, we see it highlight here, it is going to have to do this queue lookup because it's going to know, hey, I need the queue for the module that is responsible for this channel. And there is a VI specifically for doing that lookup, so it's not like it's difficult. But we just don't need to do that. And saving a little bit of time on initialization is always good. API, this exposes behavior for the entire application, and it is shared pretty much everywhere. This gets passed in most places where it's needed. So, you know, in a larger application, the 1,000 or tens of thousands of components that need access to the API aren't storing copies of it. It's not the biggest class, but it does have quite a handful of things in here. So minimizing the number of copies of that are needed, probably not a terrible thing. So this gets passed into most componentized and abstracted code. Group, this is the group of data that belongs to this, to the control module. So control module, you're typically going to see the module definition, top level itself, some of the module level configuration, and then a group. So this is any named object that has a VL type of group in its nested meta. And then everything inside of a group that is a channel that gets published as part of that group and will be in that group's value array. So that's that group, and we can use that to look up the channel indexes, and then config element. This is the entry itself. So this is going to basically be this subtree of this JSON configuration tree. It's gonna everything starting. It's this entire object, but that object is named, and all of that is easily accessible. If we needed to, this could reach up the tree and find other things it expects to know about. That happens a lot with some of the modules and the GUI components. However, these control components are much simpler in that regard. They shouldn't be doing that very often, but they could if they needed to. There's nothing preventing that from happening. But that config element is what's going to let us traverse down to these known named elements, and then we can use the group to get the indexes for the channel values. So we're going to look up a child by name. I'll do this once from the automatic palette. And I'm going to leave that config up so I can more easily see all these names. And so we're going to get the value we don't need to get. That is, value fields are handled specifically by the configuration library. And that's actually also going to get handled automatically by the group. This is what sets the default value for the root channel. And that's the same thing for this. These values automatically become the default for these channels. So I don't need to do anything special with the value field, but everything else pretty much will need to. So we're going to start with the output. And what we get out of this lookup child is not the value for that, it is the child node. Now, we can safely assume that it is a string. So there are a bunch of properties to get these values as different types. And these even have the ability to convert from some different types. So if it's a number, we'll do the string conversion for that. If it's a Boolean, we'll do a string conversion for that. If it's a string, cool. We just need to pull it out of the variant. And anything else, you're going to get the empty string back. I should probably generate an error here. That'll probably come in as soon as I get bit by that. Or somebody else lets me know they get bit by that. But we can get that string out. So that is going to get stored as the output name. And then we're going to need to get a handful of other things. So the process value is then going to get looked up. And this one we're going to see, because one of the things I want to support is a single value. And then PV calc wouldn't need to get set because for a single value, there is no averaging or median or any other operation that really matters. But I also want this to be a valid configuration value. So we're going to need to be able to explicitly handle both situations. And I already do that in the header code, so let's refer to that. So in the header code timed init control, we can see we're getting that value out. There is a property that says what is the value type, and this can be string, number, bool, object, or array. These are kind of all of the supported values, which are basically the types of values you can get in JSON. JSON is the primary format right now, but there is also support for SQLite or INI files. But yeah, so we can see if it's an array. We'll then recurse through the nested children, which should all be strings. If it's a string or any other value, we're just going to try to read it. Since we are supporting multiple process value names, we do have to turn it into a single element array. And if it's anything else, we'll let it fail. And then a lookup later on would fail. So we don't have to do any more explicit, like, will this conversion fail or not? I'm going to let that fail downstream. And that's me kind of being lazy, but that's my choice. So I'm going to copy and paste that. And I will probably have to spend a lot of time working on the layout of this VI because this is going to get pretty big with some of the things we have to look up. Potentially. I don't know. Maybe everything will be tidy enough after this. So the PV names, go ahead and grab that. I'm also going to grab this bit of code for... Whoop, I did not need to close that. And we're going to change this to the one in bang bang control. That's not what I wanted to do, LabVIEW. I think I'd rather have the string value go up instead of the error go up and back down. So there is our pvcalc configuration. And I'm going to say this doesn't need to get configured. A default value of average will do the thing we care about. In most cases. And then if it's not doing the thing you care about, well, you test it and then go, oh, I need to fix that configuration. So I am going to be lazy with errors on that part as well. And then what else do we need? We need invert and normal output. This is going to be a value bool. I'm also being lazy with the error on these retrievals. Not all of them will return errors if it's the wrong type. I will make this more consistent. The other VI we looked at was a little bit different. But I'm assuming so these lookup child will return an error if that child name doesn't exist. I'm assuming if it exists, they set it to the right value. Of course, that doesn't help with typos, but that's so maybe for the booleans, if you accidentally capitalized it or your cat walked on the keyboard, it'd be a good idea to have better error handling on that. I will opt to make my future debugging life a little bit more difficult instead. We're going to need all of this one more time. Oh, almost gave myself enough room. So that's the configuration all handled. Now we're going to need the index lookups. So we just need to look up 3 things. And you're probably curious what the third one is, given that there's only two parameters for this. But we'll take a look what that is when we get there. So we're going to get these two. So we're going to need to do meta lookups on this control param field. as is as is habit at this point, that already exists. Um, and in fact, there's a helper function for it that will look up the channel index of a control param meta value uh, in a configuration element, and then do that channel lookup based on that channel name in the group and give you back the index. So we're going to use this. So the primary input is the group. It does need the config element. And then these are going to have their property name. So that's upper limit and lower limit. And so upper limit index. Lower limit index. And then we need this value index. So that's going to be the index of the element itself. And again, this basically is the enable disable value for the entire control element. And we need this index so we can properly report back whether we're actually enabled or not after receiving commands for enabling or disabling. This is we get its name, and then we're going to look up the channel index ourselves. And this might look a little funky, because what this means is this entire object is a channel, and it's got channels nested inside of it. And this library doesn't care. All it cares is that these channels are encapsulated in a group somehow. And then the group will just find all of the channels that are contained inside the group, which happens because they're tagged as channels. So there is no limitation on specific structuring of the configuration. And this makes it really easy that I don't need to code an explicit enable disable element. If I just treat this entire node as a channel, uh, I partially get that for free. And then that reports really nicely when we're looking at the telemetry coming back from the system. You would see bang bang 1 is going to have a 0 or 1 value based on if it's turned on or not. And some of the other control examples that I was showing off in the GUI in the beginning, that's exactly how all of these ones work as well. So I know if the sequencing control is turned on, and it'll stay turned on until it's finished commanding the second value, based on this value. And that also is the value you can command to turn it on. So you just, it simplifies a bunch of behaviors and makes things very nice in how you can chain behaviors. So is there anything else I need here? Let me spot check this. So we should definitely do reporting an error. We're not creating a PID instance, so I don't need to do something like that. And then, yeah, so just using the API to report the error if there's any errors. This one isn't specifically meant to do the control message queue, so do not care about that. Some of these control elements, like the periodic control, do explicitly intend to be triggering other elements. So not 100% sure, but we might see in the periodic control implementation that it is always explicitly storing the control message queue so it knows what queue to send a command to when it needs to. But that should be it. So let's go ahead and do the report error from the API class. And that will just about wrap up this part of the initialization. And just do a little bit of feng shui. So the block diagram window doesn't need to be so big. Now, one of the things that we need to do is be able to get the process value values anytime we're updating the state of the bang bang control or assessing the state of the bang bang control, as well as the output name. You know, what channel and what other module is the command getting sent to update the output state. Now, we don't want to do this in this init control. Init control gets called typically when the entire application is initializing. And when that initialization is configured in the config file, one module at a time is running through its initialization step. And then in the case of this digital control module, it is iterating over all of the configured control mechanisms and calling init control. So depending on what order things start up in, the values that we're looking for may not have been created by the module that is responsible for it. So I am doing a little bit of a trick here where I am forcing startup order by putting a little number at the beginning of the group, the module name. Since these do get stored in a map, they get sorted by name. But there can be issues. I do want to clean that up so that it is not required. I've got a couple of things to fix to really clean that up. But eventually the idea is if the digital control module starts before the digital output module and these channels haven't been initialized yet, we need a different point in time where we can wait a little bit of time for those to get created. And so that's what the prepare control VI is for. So init control happens during application initialization. If all of the init behavior succeeds, the application continues to start additional modules. And as those modules complete their initialization, they get launched to their loop VI. And a digital control module, we can see that in its overrides. It's going to have its initial init VI called. If that succeeds, then it goes into the loop VI, and that loop VI is running asynchronously and in parallel. So other modules can continue to get initialized, create their groups, things like that. And that is effectively what prepare control is for these control mechanisms. So in prepare control is where we can do lookups. And since this is going to be just about identical from the heater code, I'm going to copy and paste and be lazy. If I end up doing this a couple more times, I will end up making helper VIs to simplify this down to 1 or 2 VI calls. But for now, this works. I'm hesitant to, again, referring to the "it's a trap" meme. I'm a little hesitant if I've only got 2 or 3 things and I haven't run into something yet that is drastically different or even subtly different, but a pain in the butt to handle. I'm averse to starting the generalized functionality before I know what that difference is. And I am not a wizard with a crystal ball that can predict things that well in advance, so I just don't. I err on the side of copying and pasting a couple of times until I know what that difference is, and I don't get myself into a trap where I have to re-implement things anyway. I'd rather copy this entire block diagram, delete it, and put down the two VIs I know I need than kind of re-massage the structure of the entire thing in a handful of places. Uh, that's my story, and I'm sticking to it, and that'll probably come up a couple more times. So bang bang lookups. So this is all going to be very similar. So I'm also going to copy and paste this PV channels array and the message queue. I will be a little bit more helpful in this class and call it the, oh, that's way down there, and call it the out message queue. And now I can specify those. So we can use these PV channels to get the current values. And we're using the actual channel object in this case because these are getting updated from some other asynchronous bit of code. They might need to go through scaling so that other code handles all of that and they get scaled before they get updated into the by reference group. So here in this bit of automation code, we get to just worry about what are the engineering units of things and don't have to try and like pre-scale configure control parameters, which is, I've done that once. Never done it again. It was very early on in my LabVIEW career. Oh, I don't want to close the project. So that is all the initialization behavior handled. Now there is handle command, and this is where this is going to receive a true or false, which most of the time means is it getting enabled or disabled. And so we are going to need one more data type. What state is this in? And this probably could just be a Boolean tracking whether we're enabled or disabled. I do like to have enumerations just in case that very often spills out into more than two states. And I already have an idea of how I would implement this in multiple states. So let's do that. Always start off with an idle state with these. Well, not always, but so far, I've always started out with an idle state. I'm going to go into a start state. So anytime we receive a command to turn on, we'll transition into this start state. And that will let us see if we should be ramping up or ramping down, or if we're already in the middle of the range, maybe do nothing. We're going to have a ramp up state, ramp down, and a disable state. Oh, no, we need a hold and a disable state. So these are, it's not quite a state machine. I'm definitely kind of intermixing states and transitions. But for an entire iteration of execution, it will be in one of these states. So they still count as states, even though some of them sound like transitions. You can have transitionary states, intermediate states. So go ahead and save this. And put that in the class. So if we're getting commanded to true, we're going to start. And this will be okay. You might see like a little hiccup if you were already enabled and you send another enable command. But that would only be for one iteration and shouldn't really affect anything critically. But this VI is going to be super simple. One of the things I could do is ignore, if we're not in an idle state, ignore trues. And if we're not in a not idle state, ignore false. But like I said, it's not really going to impact the behavior of this that much. So I'm not going to worry about that too much at all. Is that like a 60% of the time it works all of the time? Oh, and we need the control type string. I already went on the rant of why I have this VI specifying a string when I could theoretically derive it from the class name. If you care about that rant, I won't repeat it here. Take a look at the implementing the slider control video for that justification. But that string will be what matches this type string in the config, and that's how it can figure out which class to do the factory method pattern for. So that is almost everything. There is one VI left. This is the check action VI. And as I walk through with the heater, this is what does the actual, each time step that this runs does the logic. And either generates a command optionally, maybe updates some fields in the value array for the group. But for this, it's going to be relatively straightforward and simple. So there's two things we always need to unbundle at the beginning. It's what state we're in and the value index, so we can always report our current state. And the pattern I have for this is there's always a replace array subset. And this is driven by the value index. And then based on what state we're in, we'll decide what our current value is. And then, of course, a bunch of these are going to need those values. So we'll go ahead and start with that. Add a case for every value. Get rid of the default. And when we're idle, we're not on. So we'll throw that out there. When we're in the disable state, we're not on. Technically, we will still be on during this state. If 50-50 if you want to report this state as still enabled or not. Because until we pass out the action, it's not sending the command to turn off the output. But this at least signals that we've gotten to the disabled state. And actually, I need to pass the class through the case structure because some of these are going to modify our internal state. Such as the disable state, we're going to handle the things we need to handle and go to an idle state. Which is effectively the do nothing state. Now, the point of this is, one, we're doing a little bit of state management for the class data, but also we are deciding whether or not we need to send a command out, which is handled in this action. This always sends a digital command. More specifically, it groups everything going to the same message queue and collects them into a digital multiple command. So it guarantees that anything for that control iteration that updates to updates values handled by the same module. For instance, a digital output module is going to have a whole bunch of channels it's outputting. Typically, if you're using like a 9403 or 9476 or one of those different serial modules, they've got 32 channels in them. So very likely that a whole bunch of different of these digital control components are going to be coordinating controls for several of those output channels simultaneously. And we don't want those potentially getting updated at different output intervals. We want them all updating together as much as possible. That is automatically handled by the digital control module. All this component needs to do is let it know, hey, do you need to send a command? And if yes, what's the channel name? What message queue does that command get sent to? And is it a true or a false value for that digital command? So for a whole bunch of these, it's going to be, no, we're not sending anything. For start, start is going to, you know what? Let me do it this way. Yeah, so let's make a private VI. Oh, nope, don't want to close you. Since we're going to need to generate this command from a couple of different places, and it's going to depend on that invert and normal behavior configuration. So it's going to depend on these as far as what does this value get set to. We might as well make a wrapper for this. In fact, do action that's always going to be true from any of these states. Also, I should make sure I set the class banner. I don't think Bang Bang's going to fit. Nope. So it's going to be BNG, BNG. This still kind of doesn't fit, but we'll go with it. It's differentiatable enough. And in any state where we're going to be generating an action, I can just use this VI, and that'll prevent me from repeating all the assessment of the invert and normal and all of that. In the start state, we will always be generating an action because we are always going to be making sure the output is on or off or whatever that maps to ensure we're staying in that state. At this point, control, bang bang control is active, so we'll set that flag to 1. I did mention that even booleans are always represented as a double value. 0 is false, anything else is true, but the normal convention is 0 is false and 1 is true. But just as a sanity, in case it accidentally gets to any other value, anything not 0 will be treated as true. Not every state needs to generate an action, so we'll make those default values when unwired, which means that do action is false, and that behaves the way I want it to. Hold. This one's going to be pretty easy. We will eventually have some logic in here to decide if we need to transition states. So actually, let's do that. So we've got all of our PV channels we're going to need to read from. And if we look at the heater controls, check action, I've got a sub VI here for doing that. I'm going to basically copy and paste this. And this will do the averaging or the median. It does filter out values here. Eventually, I will be adding in more configuration for these to what to do if values become invalid. What is the fail-safe behavior if we don't have values to calculate from anymore? For now, this entire mechanism is meant to run on the same system. I do not need to capitalize all that. Run within the same application that hosts the I/O driving it. At some point when I get to a situation where there are control components that can get data from other remote systems, and in fact, that wouldn't even change this code. These current values coming out of this could be getting set via a subscription to data coming from another system. However, I haven't gotten there yet. I am going to have to change this when I do get there, which means I am going to have to change this here and in the header code. By that point, more of the pattern hopefully will have shaken itself out of the ether. And I will, at that point, go, okay, here is the air quotes standardized way of doing this. Of course, you don't have to use, you're not forced into using the standardized way if you have to do something subtly different or majorly different. But I will now know what that pattern looks like, so I will make that reusable code. For now, this gets me what I need. Except where did that PV value go? There you are. Copying and pasting terminals on the block diagram. It's Schrodinger's front panel element of if it's in view or out of view with LabVIEW when you paste. So don't need to do that there. And what I do need to pull out is the upper and lower limits. Now, these aren't getting read in at the beginning and then stored once. I am using them from this values array so that they can be tweaked. If we need to adjust them while the program is running, this values array is always whatever the latest commanded value is. And I don't have any code in this bang bang control class for handling those values updating because the digital control module itself is managing this values array, and it is what handles the analog command for updating those values. So I don't have to worry about that in the individual control code, control element code. The module handles that for me. So we've got the upper limit and the lower limit. While we're in a hold, I'm first going to check to see if we went to the lower limit. And so is our process value less than the lower limit? We'll do that check first off of an arbitrary decision I just made in my head. We will need to potentially change state depending on this. So we will wire the class through. And we're going to use that sub VI for creating the action. And we will be sending that action. These actually will both get wired in both cases for this outer case structure, but meh. Leave it as is. And we're going to need to set the state to ramp up. We're below the low limit, so we're always going to be going up. And then this create action can look at, are we in a ramp up or ramp down, and those other config values to know what action to configure. That's it for this case. If we're not below the low limit, we need to check if we're above the upper limit. And if that's the case, If that's not the case, not going to do anything. But if it is the case, we're going to create an action. This is the one that's going to be optional. And we're going to say that we created an action. And let's set the state to this. Actually, I'm already because I'm in a bunch of these places. I'm going to need to be setting the state before calling create action, and there's nothing that enforces that behavior. So wouldn't it be nicer if I just specified the state in create action? And then that can update the class for me. And then start always wants to go to, actually, the way we can do a start action really easily, start does not have to make a decision on what the output state is. Start can always go to hold. And if start always goes to hold, that means we don't need the start state. So I'm going to make that change. Of course, that broke some of this. So get rid of that case. In the handle command, we're going to make sure we go to a hold state. Because the hold state always makes the decision, and that iteration will send the appropriate command if it's not in the middle of the deadband. So now this becomes our start state, and we'll sit here and do nothing if we're not out of range, which is exactly what we want. Cool. And if when we're starting, we're below the upper limit, or we're below the lower limit, we try and ramp up. If we're above the upper limit, we try and ramp down. So that's all handled nicely with this. So ramp up and ramp down. Basically, the only thing they're going to need to do is decide when to go into a hold state, and that's it. So ramp up, we ramp up until we are above the upper limit. So we're going to pull out the value for upper limit. We are also going to calc RPV. There's going to be a conditional. This, of course, is 1 because we're active in control. And if we are greater than the limit, we're going to go to the hold state. That's not what I wanted to do. If we're not above the upper limit, we make no changes. And ramp down is going to look very similar. So I'm going to delete this case. I'm going to duplicate this case. lower limit index less than, and cool. Now, now that's done. Disable. This is gonna get turned into the same thing as almost everywhere else. Create action. Go to the idle state, and this will generate our action for us that makes sure we are properly commanded to whatever the output signal is. And what still doesn't idle? Doesn't have something. This is now, once I fill in this create action VI, this is the entire logic. So we have all the transition logic in here now. I just need to work on this create action and deciding the state, the actual command to send. So come in here, first thing gonna do that happens every single time is store that state value. And then grab our invert and normal. And so this VI represents the transition command that we're generating. It would probably be a good idea to generate an error if it's one of the states we don't care about. Like we'd never generate a command to go to the disable state. But I am going to throw that in with idle. Delete this case. Brain decided to take a quick nap there for a second. So when we are going to a ramp up state, we want to be true unless we're inverted. The other thing we're going to need is what is the output queue? And what is our output name? However, these do not need to get decided every time. So in here, we're just deciding what is the combinatorial Boolean logic that decides if the value is true or false. Hello, thank you. So channel and message queue are invariant to the state. That's not what I wanted. That's what I wanted. And all that needs to be done is determine what is that value inside the case structure. So channel is the output name. Output message queue is the message queue. Really some mind-blowing stuff there. And now we just need to figure out this value. So for ramp up, we're true unless we're inverted. So we're just going to negate the invert. On ramp down, it's off unless we're inverted. And hold is going to be normal. And idle disable is going to be normal. So actually, I'm going to throw that in here. Get rid of that extra duplicate case. Oh, nope, that's not what I wanted. There we go. I'm going to make myself a note here. Ramp up. True, except when inverted. Ramp down. False, except when inverted. Idle, disable, hold, normal value. And I very likely might need to factor this normal value into ramp up, ramp down, or hold, or invert. Like this is definitely prime real estate that's gonna need to be reworked, but we'll see what that does. That's everything. This should now be functional. One of the things I do in these libraries is for the stuff that I am providing as part of this repository or any of the repositories I'm creating, is a lot of these libraries will have a cube drop VI at their top level. Since a lot of this does use the factory method pattern and other factory patterns, these need to be available, and I'm doing that via what's available in memory. We need to make sure they're available in memory. So I've got VIs to drop these in. And then when you're making your application VI, well, that's a bad example. When you're making your application, oh boy, both of these are bad examples. Okay, so the GUI one is simple because I'll just need to drop one of them. You would go to the GUI elements in this case, and it's got a cube drop. And I actually did not update this one as part of the new control I implemented previously. But this will make sure everything is available in memory that you might want to use from this. Since this is just configuration, somebody could update the configuration or a plugin GUI to use a component that's available in the source code repository and that may not be available in the build. So the safe answer is use the cube drop from any of the library you're using functionality from. And if you need to do something different, of course, you're not forced to use that. You can do your own cube dropping in whatever mechanism you want. So this is what would be needed, to use the GUI elements. And since the GUI elements rely on the plugin GUI functionality, they are plugins for the plugin GUI functionality. That gets cube dropped as well. So this one cube drop gets you all of your plugin GUI functionality, at least with what's included in these standard GUI elements and the GUI library. If you had your own library of GUI elements for custom implemented behavior that isn't part of Volatus more directly, of course you would cube drop whatever came from that bit of code. The DACMX one needs a little bit more. So this one should really have Volatus DAC. This application is also what's presenting the GUIs, the generic GUIs that have those tree views with the current values. So we should drop that down. Where is it? DAC generic GUI, there it is. Oh, I don't have a cube drop for this. Let's make a cube drop for this. And now we can just cube drop this to make sure when this gets built into an executable, LabVIEW knows to include these classes. It additionally uses the data functionality. However, I don't have a cube drop for this yet. I probably created that in my other copy of the code I'm using for work. But all of these classes always use the Volatus data. So if I drop the DAC cube drop, I shouldn't also need to drop Volatus Volatus data. That's not what I needed. But I will make sure all of these classes are included. I should probably, like, I could cube drop these, and at some point I might add these in because from what I can tell, all versions of LabVIEW still have some issues detecting dependencies of interfaces. And if we go to, can't go to the parent class because it doesn't have a parent class, but it does inherit from an interface. And LabVIEW seems to have trouble detecting dependencies of interfaces when it's compiling code. That might be fixed in 2025. The problem still intermittently exists in 2024. I haven't tried 2025 yet, but I'll leave these out until I need them. These classes are directly referenced in these modules, so LabVIEW should be able to tell that they're needed. But I don't know. I've seen that it fails on children of interfaces. Now I can use this cube drop in my Volatus DAC cube drop, and I don't need to make sure those other ones. And now in my application, I don't need to cube drop this one. So now this DACMX test, if I built this to an executable, it should have everything it needs. This VI is directly from the core. It is a VI from this class, and this class directly references all the stuff it needs. So this should be sufficient for ensuring executables get built with everything they need. So let's configure. Well, I did configure a bang bang. So I've got these values. So let's update the GUI to get those. And I'm going to make this GUI bigger. And I'm going to make a handful of copies of that slider that I implemented. In the other video. Just doing things in random order based on what my robotic mouse clicking decides to do. And we're going to need something to turn on and off the bang bang control. Yeah, that's fine. We'll leave it like that. And let's get some parameters for the upper and lower limits. Double clicking that does not get me the description, the properties. So this was bang, bang, 1, upper limits. Make another one for the lower limit. Now, one of the things that might be nice to add to these control libraries is have a value meant to publish what it is using as the calculated process value. So like bang bang and the heater control that might be doing calculations on multiple values. Wouldn't it be nice to know what what value it's actually using as its decision. So I could very easily do something like this. And be able to get that published so we could display that back. I'm not going to worry about that just yet. Now this graph's getting kind of crowded, so how about I make a new one? Actually, how about I copy and paste this one? And horizontal layout for the plot legend is absolutely horrendous. I regret making that one that way. Let's do PV1, PV2, 3. Let's do enabled. And let's do output. And I will update the list of tags in here. Bang bang PV1, bang bang PV2, 3. Again, the control name itself is the value for whether it's enabled or not. And then in this case, we're using pulse1 as the output. Did I leave that closing bracket? Okay, yeah, so that should be good. So now this bottom bit of code, oh, I need to update this. You're going to command bang, bang, 1. And I got all those set. So fingers crossed, will this work? Or will I get a whole bunch of errors? It's likely got to compile some code as it's loading VIs with the new functionality. There we go. So there's the new bang bang process values that I added into the output module. We're going to want to watch pulse 1 turn on and off. And these we don't really care about. If I close that, it's going to close the application. We'll just leave that as is. Now let's get the GUI launched and see what doesn't work. These are all stale. All of the heat PVs are stale. So that tells me that that module had an error. Now what I should have done is in this application, I'm going to turn on the debug GUIs. This does go into a file in a specified folder, the events log. I don't want to navigate through disk, so we're going to run this with the debugging GUIs enabled, and now I can look for errors. Oh, wow, cool, a DACMX error. What you got for me? Task name specified conflicts with an existing task name. That is because before recording this video, I probably didn't shut something down cleanly. So we're going to fully close down LabVIEW and restart. And this is probably going to turn into a 2-hour video by the time this is done. If anybody is still hanging in there with me, besides my coworker who's going to be using these as training videos, thank you very much. You're crazy, and I appreciate you. Okay, so let's try this again and see if that error is gone. Hey, no error this time. Oh, wait. Nope. Different error. Physical channel does not exist on this device. Cool. So it is very likely complaining. Oh, mod 5. Oh. These probably do just expand out. I was thinking of these high-speed analog input cards where there's only 4 channels per card. Yeah. Let's try again, shall we? Now is it going to tell me it's a repeat name? Yeah, now it's a repeat name. Okay, so that's actually a bug for me to fix right now. DAC code, if you fail, I need you to clean up the task. Because now I know that, well, it makes sense. We've already configured it and everything. Module cleanup. Should I just do that in here? I wonder if I can just call that in here. Make sure it's stopped and cleared. And just in case it didn't successfully start, I don't care if those either of those generate errors. And then I don't need to worry about handling that there. I should do the same thing in the other DACMX tasks. Oh, look at that. I already, I just forgot it on that one. Nope. I only did it on one of them. Must have been the one where I had an error like that before. Now that task does exist, and maybe somebody can let me know how to get it closed after the fact, but it exists, and until we unload the DACMX TLL from memory, I do not know how to get rid of it. So I will close and reopen LabVIEW, and we will have to wait just a little bit longer. That's okay. Let's. Maybe this is only a 4 output. Oh yeah, does this set as a 94, 9265? I forget. Let's see what it has available. 9263. Oh, I should have looked at the pinouts. Yeah, it's only got 3 channels. Let's see. What other modules am I using? So that uses 5 through 8. Mod 1. Let's make Mod 2 another one of these 9263s. So we're going to configure the chassis, another 9263, please. What's the digital output? DigitalControlModule. I don't know. I know 9263 will work. So now let's change these to mod 2. However, this time I should be able to just run it again and not get the in use or existing task error. Yay, everything's happy. Okay, now let's run the GUI and see what errors we get here. Wow, nothing's blue. Upper limit and lower limit set as configured in the config. Pulse 1, we're going to see... No, that's a lie. We're not going to see that. Let me add something to this GUI. The reason why this one wouldn't work is because this is actually tied to that pulse control channel, not the output value itself. But now we've got a little indicator that tells us when it's on. So if I enable this, we're below the upper limit. So it is going to, or we're below the lower limit. I could turn that off. It turns off. If I start between the two of them, it should not turn on. Why? Controls. Bang, bang. Check action. I gotta go to the reentrant, clone first. And now I can watch what it decided to do. So turn it off. We can see that it is in an idle state. And when we go into the hold state, that is the lower limit and the upper limit. And let's see what it decides to do. So lower limit was true. So it went to ramp. What is the lower limit? Oh, my PV calc is foobarred. Oh, duh. I'm a dummy. It's median. So it is picking this, it's picking one of these two zeros, presumably this middle one. So we're going to set that one all the way up. We're going to set this one in the middle. And with this one in the middle, it should pick this value. So now I can move this one to whatever I want. It'll always be the median value between the other three. So we're going to turn that off, turn it back on. Hey, look, there's a proper PV value now. So actually, it was working as intended. I just forgot the logic I implemented. So now, if I... Oh, why is that graph not updating? Presumably, it is fine, because it didn't highlight in pink. If I go... So the output is off, so in a normal operation, of like a fill operation, it should stay off until I get below 2. So it turns on. That should cause it to start going up. It's going to stay on until it gets above 4. And now it is going to stay off until it gets back below 2. And so there's the bang bang logic. Let's see, I said this was maybe going to be up to a 2-hour video. I've got 10 minutes left. Let's see if I can figure out what's wrong with this chart. Cool, so the class actually works just fine. Pebcac. In here, I'm going to tell this GUI app to turn on its debug GUI and hope that that shows me an error Yep. So I totally have a typo somewhere in the configuration for that, which should cause it to highlight magenta. It's weird that it's not. Let's see what I screwed up in here. Double quotes. Now, of course, this isn't meant for editing JSON. This is about the worst way to do it. Pasting it into VS Code, it'll probably eventually recognize that it's JSON. Maybe. Maybe not until it gets saved. Ooh, how tall is this window? Let's give VS Code a little bit of help and tell it that it's JSON. And go through until you see wrong color highlighting that you would expect. So this stands out a little bit better than when everything's black and white. And once everything's valid, no more red marks anywhere. So that's my preferred way of checking JSON. And then I could just replace this. Yeah, that should have caused the background of that graph to change pink, but hey, there we go. So I can turn it on. We can see the output value turned on. Output value turned off. Until we get down to 2. There. There. And let's get some lines in the chart. It'd be kind of silly because they're not going to update very frequently. But let's get lower and upper limits in there as well. So there's our upper and lower limits. And so when I turn this on, the white line, once it crosses that, we'll see the light green changes state. And I can change these limits in real time. So now that lower limit is at 3. And as a sanity check, let's get into a hold state, stay in the middle. I'm going to lower this to 2. We're still in a hold state. And if now I'm below where it would turn on, and I change it, it always reflects the lower limit because we're always rereading that every iteration that code is called. So there's some really simple bang bang control implemented in this digital control framework that is part of the Volatus application framework. And this is the path for creating more and more configurable behavior. I now never have to drop this code anywhere other than making sure it is built into an application, and I can just configure it when I want to use it, attach some GUI element to enable it, and I could just start building up this more and more complex system behavior with all of these nice small little Lego blocks. Just for one last thing, I've got 5 minutes left till my arbitrary 2-hour limit. I do need to shut down this other application. We've got all the errors fixed, although now I'm going to be adding more config, so I should probably leave these on. But let's do one more thing. Let's say this bang bang control needed to actuate 2 valves. Let's say we're doing some tank fill, and because of the plumbing coming in, we needed to open 2 valves to get enough flow for the fill speed that was desired. So let's do another control component. start with all of the boilerplate. Why are you outdented? It's being weird. So there is, I mean, you can see it right here. There's already a component that will take a single command and mirror it to multiple other elements. And so this can forward commands to other control components. Let's say you had a couple of different control things that you wanted to enable at the same time. Maybe you've got multiple tanks that you need to fill, and if you're going to be turning on the fill automation, you're going to be turning it on all of them all of the time. You didn't want somebody to remember to have to click 3 buttons and maybe they forget the third one or the first one, or I don't know what the situation might be. But you want a single control. They're turning on that group of automation or turning it off. So since it all uses the same digital commanding pattern, we can do that. So we're going to give it a default value of off, and we're going to link it to pulse 1 and pulse 2. And that's it for this. So now we're going to update this output to BB multi. And now anytime this sends an on command, it's going to get sent to this mechanism instead. Anytime this receives that command, it's going to immediately forward it to the pulse 1 and pulse 2. And now if I run this, we should see... Actually, let me add another one of these. Link this second one to pulse 2. Go ahead and run this app. Run this app. And now they both turn on. And we can see that reflected. Where's my digital outputs? So now they're both turning on and both turning off. Oh, again, I need to set up the median value correctly. So that's an easy way. I don't have to make the bang bang more complicated and handle multiple outputs. There is a configurable component for doing that logic of mirroring that command to multiple outputs. I could probably end up doing something similar with some kind of input logic where something needs to get commands from multiple sources or verify the state of multiple sources to generate an output value. But again, that's the whole idea with this is create these small building blocks that can be combined and chained to get the higher level, more complex system behavior. And now it is all reusable, and configuration can sometimes be a pain in the butt. But as standard patterns start to develop from systems, you become aware of what the common tripping points are, and running into those less and less, and just establishing those patterns that are easily documented. But yeah, I am 30 seconds out from the 2-hour limit. Thanks again, anybody that made it to the end. If you did, you're amazing and you're crazy, and I appreciate you. If you have any questions or any feedback, let me know in the comments. This is also going to be training video for any of my coworkers that might start using this. But yeah, we'll see you next time.